Hello and welcome back after the break. Before going on the break, I had told you about the 3-bit shift register and how this can be modeled, and this was the particular slide. Now this could also have been written, if you look at this could also have been written as a single statement without the begin and end by just concatenating Q2, Q1 and Q0. That means on the left hand side I will have a concatenation operator with a flower brackets. I will write Q2 comma Q1 comma Q0 and close the bracket equal to 3 tick B000, or I can write 3 tick B0 also. Else begin here also similarly, this could be a single statement in which Q2, Q1 and Q0 could be concatenated, and here also all these three could be concatenated. Therefore, I will get Q2 comma Q1 comma Q0 concatenated is equal to D in comma Q2 comma Q1 concatenated. Concatenated means having the flower brackets on both sides. So this could also have been done that way, but that would have been a little bit confusing for the newcomers. So I have chosen to write it in this particular way. Then let us look at the synthesis aspect. This slide I should have put before the break, but let us go ahead. We have critical paths in the timing, and the timing report from the synthesis output will also tell what are the critical paths, what paths are close to the time period of the clock. The path delays are close to the time period of the clock. That will tell you, and from there if we want to optimize or if we want to provide some cushion to these particular areas, then we can perhaps set the maximum delay from one point to another point as being much less or much less than the clock period, and then run the synthesis once again, so that the synthesis tool may now try to meet these specifications which have been given in the constraints, and it will try to put larger cells with a higher drive strength to reduce the combinational logic delay in such of those paths which are coming very close to the clock time period. It is important to automate the synthesis flow also, and therefore scripts are written for the synthesis, so that once the design is given, then the whole thing gets automated. And if there are certain other things like some names, type of names have to be avoided by the synthesis tool, then we can give our own kind of names to the outputs, saying that this output must be appended by this much this particular string or something like that can be done in the synthesis tool. Then the technology library itself will have several different views or several different functions inside the technology library, and these functions are used at different points of time in the manufacturing flow. The first view or the first information, data, whatever you call it, many people prefer to call it a view, okay, is the Boolean view used in verification. Boolean view means if you have a 2-input AND gate, it will say that the functionality of this 2-input AND gate is Y is equal to A and B. Simple as that, Boolean view, without giving any other information. So this Boolean view is used to find out whether the gate level functionality is meeting the RTL level functionality or not. The RTL level functionality has been verified through the use of a test bench by applying the inputs through the test bench. Therefore, assuming that that functionality has been completely verified, we are now trying to see whether the gate level simulation also meets certain requirements or not. Therefore, the gate level simulation tests will be a small representative sample of the number of tests which have been run at the functional or the RTL level, and those tests will be run at the gate level. These tests can be run, as we have seen in the next point, we will see how they can be run. The second view is the power view. This is not being written in any order of preference or priority, is just that it is randomly written there. So power view, which is used in power analysis and estimation to estimate how much power is going to be consumed by the particular circuit when it is working at a specified frequency, it is necessary to have some power estimation software also, and therefore the power estimation software will make use of the information given for each and every cell of the technology library as to how the power, what kind of power is going to get or what amount of power is going to get dissipated. As we have mentioned earlier, the power view, the power of elements, logic elements in CMOS is directly proportional to the frequency, because frequency increases the switching of the circuit, switching activity in the circuit, and every time a circuit node switches from a 0 to a 1, there is some parasitic capacitance which is required to be charged, and the requirement of this charging needs current. This current is drawn from the power supply. So every time a node switches from 0 to 1, power is consumed. Now there was one question which came to me saying that are these what is the use of these parasitic capacitances? Parasitic capacitances are not introduced there in order for the functionality to get improved or anything like that. They are unwanted capacitances, but which are present there because of the structure, because of the construction nature of the semiconductor circuit, and their bad effects or the adverse effects need to be overcome. Okay, and we have to live with it. There is no way of parasitic wishing away the parasitic capacitances. They can't go to 0. No. So the power view, the second is the power view. The third, very important also, is the timing view, and it tells what is the delay of circuit delay of this logic element or logic delay of this element. What is the delay from the input to the output? Such detailed information, like if you have two inputs A and B, what is the of an AND gate, what is the delay of the output from A to the output when B is held at 1, okay, and what is the delay of B to the output when A is held at 1. Okay. Also for an OR gate, if we have multiple inputs A and B like that, then if A is equal to 0, what is the delay from B to output? If A is equal to 1 and B has to transition from 1 to 0, okay, is there a change in the output, or if there is going to be a change in the output, this delay, what is the delay when the other inputs are at different values? Such delays also, such information is also given in the timing view. So timing view is quite extensive, and this information is made use of by the static timing analysis tool. Static timing analysis actually is a tool that can be used at different stages of the manufacturing flow. It can be used in the gate level simulation, okay, to find out what are the, how many paths are there, because static timing analysis tool does not apply any test patterns to the circuit. It only reads in a circuit, and based on the connectivity information in the circuit, it will know what are the paths in the circuit. Therefore it tries to take the timing information from these logic libraries, and if at that stage interconnect delays information is also available, it will take that also and come to a conclusion as to whether certain paths are critical, some paths are violating the timing requirements, or all the paths are meeting the timing requirements. If they are meeting the timing requirements, by how much margin are they meeting the timing requirements? All this information will be available when the static timing analysis tool actually runs on this particular netlist. This is only for timing information. The timing information can be obtained through the use of an STA tool, static timing analysis tool. Then the fourth view there is a physical view, which is basically a footprint or the geometry of that particular cell. What is the geometry of that cell? Is it a 5 micron by a 1.8 micron cell, or is it a 2 microns by 2 micron cell, or what is the height of that cell, what is the width of the cell, where are the pins located for that particular cell, where is the D input, what is the dimension from the top left, where is the power supply rail. All those information will be available in the physical view, which is primarily used in the place and route physical design, because when you are placing the components, you must know what is the component size, otherwise the components will get overlapped and that will run into errors. Your design rule check will throw a lot of errors. Okay, and you will not be able to do that also in the first place. So you need to know where the pins are located and what is the size of that particular cell which you are using in the place and route in your netlist. So these things are the ones which are given in the footprint. They call it a footprint or the physical view of that particular cell. Now in this particular slide which I am showing here, I mentioned that gate level simulation is extremely slow compared to RTL level simulation because of the number of details that are involved in gate level simulation, and more the details, the more is the computational requirement or the computational power that is required. So the time required for gate level simulation is pretty large compared to the time required for RTL level simulation. Therefore, all the tests which were run at the RTL level will not be run at the gate level. What the gate level simulation will do is it will pick only some representative tests from the RTL level tests that were run, and these tests they will then run at the gate level just to give a degree of confidence, saying that yes, the synthesis tool has properly converted the design from RTL level into the gate level. Now I am not saying that there is a doubt on the synthesis tool, but every transformation needs to be checked, because it is possible that you may have written the code in such a way that at the RTL level the simulation works fine, okay, but there might be certain what should I say, they call it synthesis pragmas. Pragmas means they are directives to the synthesis tool. These directives to the synthesis tool may have been written in your Verilog code, which causes the synthesis to work in a different way. They are basically comments as far as simulation is concerned, but they will be directives for the compiler. Therefore, you are providing the compiler with more information or different information than what you provided the synthesis tool with. Therefore, the simulation tool with. Therefore, if the simulation and synthesis have got different information, the synthesis may synthesize to a different kind of logic whose behavior when run at the gate level simulation may not quite exactly match with the behavior of the output at the RTL level. So therefore, we need to be very careful, and therefore we need to confirm that everything that has been transformed is working correctly. At checkpoints, if you have certain checkpoints, these are the checkpoint tests. So if you run these tests and these tests pass properly, then you can say with a very, very high degree of confidence that the synthesis process and the code that was written at the RTL level has been properly transformed. Okay. So when you run the simulation, this simulation, post synthesis simulation, can be run with timing and without timing also. So without timing means basically in the command line itself, if you give a command line option called no timing or something like that, then it will not take the timing information from the cell library, from the technology library. It will not use the timing information, everything it will set to 0. However, if you say minimum timing, typical timing and maximum timing, there is a variation in the timing of each and every cell that has been manufactured or that has been characterized and will get manufactured. There is a minimum delay, there is a typical delay for most of the cells, typical delay, and there is a maximum delay also. Therefore, if you want to really check whether the timing is being met or not, in addition to STA, you can also do it through simulation. Minimum delays are useful later on when you when the sessions on physical design are conducted. You may also come across what is known as multi-corner, multi-mode, multi-corner, in which corner is basically an extreme case in which you verify or test the design whether it is working correctly or not. That is what a corner. Okay. So we will test with different corners. Minimum delays are useful for checking if there are any hold timing violations. Typical delays will tell you whether the circuit is generally going to function at the required timing frequency or not, and maximum delays are used for checking whether there are any setup timing violations. Setup timing violations occur because of maximum delay, and hold timing violations, if at all they are going to occur, they will occur at the minimum timing delays. Okay. Typical timing delays may not throw up all these things, but are first used only to find whether functionality is okay or not. To check for timing, these two corners are preferred used, they are simply used, and only a small number of tests to be run on the design at the netlist level. So what is it that you get out of the netlist, out of the synthesis step? That is a netlist, which is a software representation of the circuit that is going to get manufactured, or at least a sub block, if not the whole block, if not the whole chip, at least the sub block part of it. Okay. So now let's go to the next. At this stage, what happens is I will introduce you to the topic of design for testability. What is design for testability? Design for testability, the name is basically representative of a collection of a few methodologies for making the circuit readily testable after it has been manufactured. The circuit has to be tested after it has been manufactured. How would you know whether the circuit has been manufactured correctly or not? In the process of manufacturing, there are so many different steps: ion implantation, diffusion, maybe layer oxide, coating, etching. At the process of etching, when you are having two aluminum tracks running side by side, it is quite possible that over etching may cause the track to get cut at some point of time, or to narrow down at some point of time. If a track narrows down, then its resistance increases. If its resistance increases, typically tracks together with the parasitic capacitances form what is known as an RC low pass filter. So when R increases, the RC time constant increases and the delay increases. When the delay increases, the chip may not work at the required frequency. So such kinds of defects will be there in the chip. You not only have to test whether it is correctly manufactured in terms of trying to find out whether every pin goes to a 0 or a 1 or not, but whether it is going to 0 to 1 in the required amount of time and back from 1 to 0 also in the required amount of time or not is also to be checked. So there are different kinds of faults or different kinds of defects that need to be checked when the chip comes back from manufacturing, and DFT is a collective name for a few methodologies, maybe 4 or 5 or 6 different methodologies, okay, which are used so as to modify slightly the chip circuit, okay, not in the functional way, but for making it easy for testing. Just as on a PCB you put some test points on the PCB, okay, so that you can plug in your oscilloscope over there and check whether the waveforms are coming correctly or not. Similarly, here also you have test points not in the form of let us say lugs or something like that you put on a PCB, but these will be in terms of some cells, logic cells, which capture some kind of a data in between and internally, and then that data is then made available to the response analyzer, which analyzes the response of a particular input. So that way DFT is a collection of methodologies. And what are the advantages and drawbacks of DFT? Why should a chip get tested after it has been manufactured? Because you need to know, obviously there will not be 100% what is known as a yield. I talked about yield right at the beginning. So there will not be 100% yield. Some of the chips may not have been manufactured correctly for several reasons. There are several reasons. Whatever be the reason, they may not have been manufactured correctly, and obviously you wouldn't want to send a bad part to a customer, because obviously, and if the customer receives a bad part, maybe 2 bad parts out of 100, then the customer starts saying that, oh, this manufacturer has supplied bad parts, okay, and the name and the fame of the manufacturer is at stake. Manufacturer has to be in business. Okay. So to be in business, they need to identify which are the good chips from the bad chips, and they need to test those chips once they have been manufactured. Mind you, verification at this point of time, I will say that verification is different from testing. Verification is not the same as testing, though loosely whenever you are doing a verification, you say you are testing. In the context of that particular statement, you may know that it is verification, but strictly speaking, verification means trying to check whether the intended functionality has been captured in the design. Testing is to check whether the part has been properly manufactured or not, or whether in some transistors there is a defect because source has got shorted to the drain, or two tracks have got shorted to each other, therefore some tests are failing. Okay. All these defects are not present in a software representation of the design, because the design has not undergone that transformation from software into silicon. When in the process of undergoing this transformation from software to silicon, then these defects will creep in from all different places, okay, and that has to be checked against, okay, or that has to be verified, tested whether the part has been manufactured correctly or not. That is why DFT is required, and DFT is not done on small parts, because DFT involves a cost. Okay. There are several DFT engineers working on a particular product, like for maybe weeks and months together, to modify the circuit designs in such a way that the functionality does not get affected, but it becomes easy for testing the circuit after it comes back from manufacturing. That is what the DFT will do. Okay. Also, let me emphasize the point here is DFT does not really look for the functionality in the design. The functionality can be anything. It could be a network processor, it could be a microprocessor, it could be a communications controller, it could be a graphics chip, whatever it is. But the vectors, or the vectors means patterns, which are applied to the chip under testing, are basically derived from the connectivity information that the tool, DFT tool, I will talk about DFT tools also, that the DFT tool generates. The patterns that DFT tool generates is based on the connectivity information and not on the functionality of the circuit. So don't be under, though of course some of the vectors or some of the tests, some of the patterns which were used at the time of verification can also be incorporated in the testing, but these are not sufficient enough. Okay. Testing requires more extensive number of patterns, and these patterns are derived based on connectivity information, not on functionality. It is important to understand this. So, what are the advantages? The advantages are that it provides a real measure to say that this chip has been manufactured in a quality way. There is some metric of some measure of quality is provided by DFT. Two chips can be said that okay, this chip is a better quality than this chip, basically because this chip has done its DFT to a much larger extent than the other chip. Doing a DFT to a larger extent means covering more number of areas to find out whether any fault is there or not. If you have not covered a particular area to find out whether there is a fault somewhere in the silicon, then it is likely that if there is a fault in that area, it will go undetected to the user, and if the user then exercises that part of the chip in some of his applications, then the user will experience failure of that particular output, or failure of that particular chip. Okay. Therefore, the advantages is that it separates the good parts from the bad parts. Okay, and obviously the good part only will be sent for packaging. Now, when are the chips tested? Immediately after they are manufactured. While they are on the wafer itself, they are tested. Okay, while they are on the wafer, chips are not tested after they are separated out, they are packaged and then tested. No, they are tested by what is known as an automatic test equipment, ATE, immediately after they have been manufactured. Immediately means not the same second or the same minute, but maybe they have to be transported from one place to another place. That will take some time, but even before the next steps, maybe they have been coated with some kind of lacquer coating or something like that, so that some of the parts, they are protected from the environment at a later point of time. So the pads, the IO pads and places to where the inputs have to be applied and the outputs have to be taken from the chip, these are actually left like that, so that the metal contacts, what is known as a load board, there is a load board, the chip is manufactured with a certain dimension of the silicon. Corresponding to that dimension, there will be a probe. Okay, and when the chip is on the wafer itself, that probe will go and sit on the chip like this, and then it will apply the test patterns to the particular chip, and the response to the chip is captured back by the response analyzer, which is also a part of the ATE. So chips are tested like this, and each and every chip is tested by the tester. And this testing happens only for VLSI chips. It doesn't happen for small chips like a counter or a 4-input AND gate, or because the cost of DFT will be more compared to the cost of manufacturing of this chip, or the cost of silicon much more. Okay. It has to be kind of much less compared to the total cost of the chip. Actually, if you look at some books, they will say that the cost of the chip is divided into 3 parts. One is the silicon cost, the other is the packaging cost, and the third is the testing cost. Okay. Silicon cost means raw material cost and all those things, cost of manufacturing, that silicon cost, testing cost, and packaging cost. So these 3 more or less in equal proportions. You can say that 33% the cost of the chip is determined by these 3. Okay. So the challenge here in DFT is to be able to test the whole chip, including its internal nodes, to see whether they are working correctly or not, only from its primary inputs. You cannot access the internals of the chip, because the chip has been manufactured and internals are so small and in the lower layers maybe that you just can't access them. So therefore you should be able to control, you should be able to apply the required input at the deep inside the chip. Okay. Therefore some hardware will have to be introduced, and some logic will have to be introduced in order that when the chip is going to be tested, it will facilitate testing in an easy way and improve what is known as controllability and observability of the internal nodes. This is very important in DFT, and the challenge lies therein. Okay. How do you get to access the internal nodes of the chip and set an internal node either to a value of logic 0 or to value of logic 1, and then see whether by applying some other patterns whether that particular node is working correctly or not, by monitoring the response at the primary output. So everything has to be applied at the primary input and everything has to be observed at the primary output. You cannot observe internal nodes because they are not accessible. You can observe them only by bringing them to the output, and that therein lies the challenge. Okay. Let us look at what is the purpose of the test. The purpose of test means testing a particular chip is to provide a measure of quality of a finished semiconductor product. Now finished semiconductor product could be either a standalone die. Standalone die means a die is basically one chip on a wafer is called a die, or it could be a packaged part. Packaged part, packaging happens only after testing. Testing does not happen after packaging, though it does in a way, yes, but 100% testing is done for VLSI chips which are immediately after manufacturing, and only the good parts are sent for packaging, and after packaging on a sample basis some of the chips may get tested. Okay. Purpose of DFT is to place additional hardware means logic elements, okay, on the die, on the chip, to enable performing quality measurements. Now when do you place this on the die? You place this additional hardware immediately after obtaining the netlist. I am putting it in a very simple way. Okay. Immediately after obtaining the netlist, the DFT engineers get to work. In fact, they do not get to work after obtaining the final netlist. They start their work even when the development of the RTL is going on, okay, and a draft netlist might be available. The first version of the netlist may be available. They will start working on their scripts. Everything is put in scripts. Okay, the script like Perl is one scripting language. TCL/TK, TCL stands for tool command language, is another. TCL/TK is another language. So they might use any of these, their preferred choice, or whatever the management has instructed them to do. They will do that, okay, and they will start working so that their scripts also need to evolve. Everything needs to evolve. Nothing comes right at the beginning and in a perfect condition. Okay. So these DFT engineers will start working on their job, and they will take a first version of a netlist and start looking at that. And then what is the additional logic that needs to be placed? That additional logic that needs to be placed on the chip is basically to improve the controllability. Controllability is the ease with which you will be able to put a value on the internal node, value of logic 1 or logic 0 on the internal node. Not just that, observability also must be there, but because if you put a 1 on a internal logic node, but you are not able to find out whether that 1 has worked correctly or not, okay, there is no use. So you should have controllability, you should also have observability. So improving the controllability and observability of nodes which are deeply buried inside the circuit is one of the challenges, and the DFT engineers have been able to overcome these challenges to a large extent, okay, and that is why we are seeing this progress over here. So in the past, the testing, that means addition of this logic or whatever it is, was not the design engineer's responsibility. Design engineers could go scot free saying that, okay, my job is done, I will give it to the DFT engineer. But these days design engineer himself or herself should take the responsibility to some extent, if not to a whole responsibility, because DFT is a specialized job, okay, just like verification. So writing verification, writing standard test benches in system Verilog using the UVM methodology is something that is a specialized job, okay, and similarly DFT is also a specialized job. So DFT engineers need to know what tools to use, when to use these tools, what are the limitations of these tools, what are the advantages, how to exploit that particular tool which is available to you. All these things have to be learnt by the DFT engineer. In addition to that, the DFT engineer must also know what is the circuit doing there, so that the additional hardware, that is logic, that is placed on the circuit should not cause the circuit to either to malfunction or to decrease in its speed considerably. Some small amount of decrease in the frequency may happen, will happen because of the additional logic, because it increases the delay in the timing path. Okay. So all these things will have to be faced and will have to be overcome. Okay. But now this is no longer the test engineer's job itself. It is the design engineer also who is responsible for the DFT performance of the chip. The advantages of DFT as a collection of methodologies. When you say methodology, basically it is a structured way, maybe an automated way of generating test patterns. You do not have to write or generate test patterns manually. These test patterns will be automatically generated. That is why we have the term called ATPG, automatic test pattern generation, okay, or ATVG, some people call it automatic test vector generation in DFT, because the DFT algorithms work in these particular tools. They read in the netlist, they get the connectivity information, and based on this connectivity information they will generate the patterns. Okay. Not only they will generate the patterns, but for every pattern that has been generated, they will also know what is the output response for a perfectly manufactured circuit. So therefore every test vector, we call vector for number of bits put together, is called a vector. Therefore a test vector is basically a test pattern that is applied parallelly to the circuit. So these test patterns, basically test vector consists of a stimulus, which is the input, and the response, which is the output. A stimulus response pair constitutes one vector. Such test vectors are applied to the device, okay, and the device then gets tested on an ATE, or also called the tester or the automated test equipment. Oh, did I? Okay. It decreases the test time. Decreasing test time directly translates to decreasing the cost of test, because the cost of test is also included in the chip cost. Okay. And methodology enables some form of automation. As I said, automatic test pattern generation. Okay, they will generate the vectors for you. You do not have to worry about generating the vectors. Okay, they will generate the vectors based on the netlist that has been fed to them. Okay, after it has been modified in such a way that it becomes easily workable for the tool. ATPG tool. Like for example, take an example of Mentor Graphics Fast Scan. This is a tool for generating ATPG vectors. Once the modified netlist, What modifications are being done here? Modifications being done here are the ones that are required for the ATPG tool to generate its vectors. But these modifications are working, or maybe are present, or I am not saying present, but they come into the picture only when the chip is in the test mode. The chip then has got two modes of operation. One is a test mode and the other is a functional mode. So when the chip is getting tested, it is put in the test mode. Once it is in the test mode, it gets tested and then it comes out. Comes out means comes out of the tester, not that it is put in the tester. Tester is not like a oven or a furnace where you put the chip inside. Okay. The chip is tested, and when it is done, testing is done, then after the whole testing is done, then the whole wafer will be diced by what is known as a laser dicing, and it will be cut into different ICs, and the different ICs will then go for packaging. Only the good ones will go for packaging, the bad ones will not go for packaging. Why should we have test? There are different concerns that are raised by different groups in an organization, maybe whether to go in for test or not to go in for test. So what are the concerns? The design engineering group will say that, oh, there is an extra logic on, there is an impact of extra logic, the impact on area as well as performance in terms of timing, okay, and power, of course, performance. Now whatever logic is modified by the test people or the test engineers, this logic will remain on the chip and go for manufacturing. It is not something that has been that the design DFT engineers will do at the time of their job, okay, and then the logic will go away. No, that logic actually sits on the chip and goes through the manufacturing stage. Therefore extra logic is there right throughout the manufacturing, and in the end chip also this extra logic will be there. Okay. Therefore this extra logic will cause maybe a very small degradation in the operating frequency. Okay. But if the operating frequency itself is much more than what is required initially, this degradation will not really cause any problems. So there is an impact. Management will say, oh, management trade-off between advantage of test and the schedule slippage. So basically DFT engineers working on a particular chip may work for maybe a month, 2 months sometimes, just to make these changes so that the testability, not only that, they need to come up to certain expectations of coverage figures. Now different types of faults are there in the circuit. You need to uncover, you need to detect and say that none of these faults exist. Okay. So basically what is known as a stuck-at fault. A stuck-at fault, a coverage for stuck-at fault may be 95%, meaning to say that for every 100 internal nodes, node is a pin. It could be an input pin or it can be an output pin of a particular gate or a particular logic cell. That is a node. So if you have 100 nodes, a coverage of 95% or more means that 95 out of these every 100 nodes need to be able to toggle from a 0 to a 1 and from a 1 to a 0. Only when they are toggling from 0 to 1 and 1 to a 0, then that means they are properly manufactured. The chip at least in those nodes are okay. Sometimes a node may internal part of a circuit may get stuck at 1. Some point may get shorted to VDD, it might get stuck at 1. So you can make it a 1 because you do not need to make it, it is already a 1. You can't bring it down to 0. So basically such nodes which cannot be brought down to 0 are stuck at 1, and such nodes which cannot be brought up to VDD are stuck at 0. So we have to see that no such nodes internally are stuck at 0 or stuck at 1. If there is even a single node which is stuck at 0 or stuck at 1, the chip is set aside, it is not sent for packaging. Okay. So these kind of tests are important, okay, whatever it is, but basically it is required contractually, as a contract it is required, okay, to be provided to the manufacturer. Like for example, let us say Xilinx is making an FPGA or Cypress Semiconductors is making some chip. This chip has to be sent to TSMC, Taiwan Semiconductor Manufacturing Corporation, for manufacturing. Now when the chip is manufactured, the manufacturer, that is TSMC, which is in Taiwan, okay, it has to know know that it has manufactured correctly. It may have its own confidence, but it also has to show to the end user that it has been manufactured correctly, because if not, the end user may take it, and if it is not working correctly, may go back to the manufacturer saying with a complaint saying that this particular chip is not working correctly in my system or in my circuit or in my setup. So what does that mean? So there is no way of telling whether the chip has been manufactured correctly or not unless the chip is tested after manufacturing. So in order to test the chip after manufacturing, the manufacturer per se does not know what kind of vectors to make or what kind of vectors to generate. So these test patterns are generated by the DFT engineers. After they have completed the DFT job, they will come with a set of patterns, each set of pattern for different types of faults. Fault number 1 type, you may have 1 million patterns. Fault number 2 type, you may have 100,000 patterns. Fault number 3 times, you may have 20,000 patterns. Like that, you will have patterns. So these patterns need to be given to the manufacturer, and then the manufacturer will take your design, okay, and then run these test patterns on the design that you have provided to the manufacturer, and ensure for himself that these patterns are working correctly and that they are giving the required coverage, 95% coverage, let us say, for stuck-at faults. If that is not there, the manufacturer will not accept your design. He says that you have to give me a 95% coverage. Only then I manufacture, because otherwise with that 95% coverage, I have the confidence, the manufacturer has the confidence that his chips will be manufactured correctly. 99% of the chips will come out correctly. With that confidence, he will go. But if you give only 60% coverage, then he will not accept that. The manufacturer will not accept. The required amount of coverage has to be there. So contractually, it is required for the customer to provide these test vectors to the manufacturer, so that the manufacturer takes your design, accepts your design for manufacturing. And therefore, second point is that it is required by a competitive environment. You know that there is a cutthroat competition these days between several vendors manufacturing maybe different kinds of chips or maybe a standard part. So now, if one vendor says that this is a quality product with a 95% coverage, the other vendor says that this product has got only 80% coverage, both the products maybe have the same price, which one would you go for? You will go for a 95% coverage product, because that chances is that product will have lesser chance of some circuitry failing somewhere in between which has not been covered. Okay. If the circuitry, the part of the circuitry which has been covered is been covered, so you know for sure that is not failing. But what about the remaining 5% which has not been covered? That 5% is like a confidence of the manufacturer that nothing will happen in that 5%. It is like when you have an analog signal and you sample that signal, okay, what do? You take the sampling frequency to be high enough, higher than the Nyquist frequency. So that basically means that in between you are not looking at the signal. You have the confidence that with these samples you will be able to reconstruct the signal at a later point of time. It is exactly like this. Look at these reasons for test. We have the positive aspects of test and the negative aspects of test. Okay. The DFT, because of nature of the structured methodology, it eases the generation of vectors, okay, although it may add complexity to the design methodology. It eases diagnostics and debugging, okay, although it may impact the design power and the package pins, because if it impacts the package pins, because DFT may cause an increase to the number of package pins. For example, there is a methodology called, okay, I will come to that later, let me not touch upon it right now, I will come to that a little later. The third one is it provides a quality metric. You can say for sure that 95% coverage I have, and that coverage will be given to you by the tool that generates the vectors. That itself will measure the coverage and tell you that this is 95% coverage I have achieved, the tool has achieved. Okay. On the other side, it may impact design speed or performance or both. Okay. Having a structured methodology reduces the cost of test, because you can automate this testing and it will reduce the cost of test, thereby it reduces the cost of the chip, although on the negative side it may add to the silicon area. It does add to the silicon area, not only for the logic cells, but there are certain signals which also need to be routed through the chip. And when you route a signal, obviously you should leave space on either side of the signal. You cannot have therefore that the routing path also occupies space. Okay. Therefore, the silicon area tends to be more when you incorporate a DFT into the chip. Okay. All these things have to be considered. What happens in DFT? I am just summing up what happens in DFT. In DFT, the netlist gets modified slightly. Yes, that is true. Okay. But the functionality remains unchanged. Area slightly increases, that is because of the additional logic. Timing gets slightly adversely affected. Adversely means in a negative way it gets affected. Okay. And in DFT, controllability and observability are the key considerations. These are the key considerations which and these have to be improved. When you improve these, your coverage will also get improved automatically. Now, it is important to understand that testing time should also be kept to a very small value, a small time as much as possible, in order to minimize the testing cost. Testing is done. Now, when you have a tester, the tester applies the patterns to the chip through the probe, which I told you sits the probe actually sits on the chip on the wafer and applies the test patterns, and the probe has got a cable, okay, which collects the response, and the response is analyzed by the test equipment itself, and then it will say whether it is as per the expected pattern or not, and then it will declare whether that test has passed or not, that vector is passed or not. Okay. So, this is how it will be tested. It takes time to test a particular chip, and the amount of time it takes will directly determine what is the cost of testing. So, it must reduce, you must reduce the cost of testing as much as possible. Therefore, there are algorithms, there are people working on what is known as test vector compression. How will you compress the test vectors, okay, such that this compressed form of the test vectors will still be able to cover or give you a high value of the coverage, low volume, high coverage of test vectors. That is what people are will be working on. There are algorithms, maybe still newer and newer methods of compressing are coming up, and one such tool called the test compress from Mentor Graphics is one in which it takes the test vectors, looks at the test vectors and compresses them. Okay. And what is the advantage of compressing? The moment you compress test vector, its volume reduces, therefore, the memory storage requirements for these vectors reduce considerably, okay, because tester has got memory. Why does a tester needs to have a memory? Because when it is applying a pattern, multiple patterns will be stored in the memory. There will be one memory bit having a large depth, let us say 4 megabits of memory per pin of the package of the part. That means every time you have to apply a bit or a pattern, it depends on the number of input pins. If you have 20 input pins, or let us say 100 input pins, you need to have 100 bits or 100 bits coming and getting applied to these 100 pins. Therefore, for each pin, behind each pin, there is a memory there in the tester, which is applying that particular vector from there, from the memory down to the pin. Okay. And therefore, if you compress these vectors, the memory requirement of a tester which stores these particular patterns, memory stores the patterns, the storage requirement comes down, the memory size also comes down. This is one of the reasons why scan vectors or vectors need to get compressed. Testing is done using ATE. I will show you how the testing is done through a particular simplified version of an ATE. We have a tester and a memory over here. This tester and memory, this memory stores the memory tester pattern. Where is this tester pattern? Well, it is loaded into the tester by the not test engineer, by the manufacturer of that particular chip who is going to test. He or she has got a tester at their site. So, this tester is loaded with the patterns that have been developed by the DFT engineers and that have been provided to the manufacturer at the time of manufacturing. these patterns will be loaded into the tester memory or into the tester, which in turn actually puts them into the memory. Then when to apply these patterns, what is the frequency at which these patterns have been applied, when to actually collect the sample or the response value, all these details are also given to the tester. Information is given to the tester through a file, typically what is known as a test procedure file. They call it a test proc file, okay, test procedure file. This is given through a test procedure file, and that file the tester reads that file and accordingly generates the signals with the required timing. When to apply a particular and it is a cycle based tester, that means clock cycle by clock cycle, clock cycle by clock cycle, the patterns are applied. The input pattern may be applied maybe 10% into the clock cycle, and the response may be taken at 90% into the clock cycle. That means if the clock cycle is at 10 nanoseconds, at 9 nanoseconds the response is captured. Maybe at 0.5 or 1 nanosecond there is the stimulus is given. So these timing requirements are controlled by the test procedure file, which causes that ATE to output the patterns at exactly at the precise timing. So they apply the test pattern to the DUT, device under test, okay. And of course you have a tester clock also, which actually runs at maybe some frequency, but typically testers do not run at the same frequency at which the device could run, because the device typically could be of a newer technology. The first thing that somebody makes of a new technology is a device, okay. The testers will come much later, okay. So the testers may not have the same frequency of operation as the device. The device could be operating at a maximum frequency of 1 gigahertz. Testers could be operating at 1 megahertz, maybe even less, 50 megahertz. Okay. Though of course these days testers are also coming out at high frequency, but by and large the testers do not work at the same high frequency that the chip can work. Why does the chip, how can the chip work at 1 gigahertz? Internally to the chip there might be a PLL, a phase lock loop, which takes in a 100 megahertz clock and generates a 1 gigahertz clock internally by doing frequency multiplication. Having done that, it applies this 1 gigahertz to the chip, and mind you, not all parts of the chip will work at 1 gigahertz. Only very few instructions of a processor could be working at a 1 gigahertz clock and giving out one result per clock. But other parts of the chip will not work at 1 gigahertz, they will work at a lower frequency, and at a much lower frequency the PCB output signals also will work. Any signals coming out of the chip will go on to the PCB, and that they cannot work at 1 gigahertz on a PCB. They will work at much lower frequencies, okay. So this is typically how the tester will setup will look like, and we have a tester clock, we have a tester pattern. The pattern, this is the pattern that has been loaded into the tester and it is applied to the DUT. The DUT will give the response at 90% of the cycle time. At 9 nanoseconds the response comes. The expected response is also fed to what is known as response analyzer, which is a part of the tester. Do not think that the response analyzer is a different kind of equipment. It is a part of the tester, and when it compares the expected response with the test response or the obtained response, then it decides whether that particular test has passed or failed. And now when a test fails, ideally you may not want to do further testing, because one test has failed and there is no point in testing further and wasting time and wasting time on that tester, and just keep that aside. When the first test that fails, the chip has failed. Now sometimes you may want to go ahead with the testing and do the complete test to find out where all these failures are occurring. If there are some chips in which the failures are occurring only at certain places, okay, it is useful information from the diagnostics point of view. It is very useful to debug why these chips are failing only at this point. From there they can work backwards and find out, is it because of insufficient doping, or is it because of some process or manufacturing defect, or is it because of some over etching, or is it random? It could be random also, because when we take the silicon wafer and then go through the process of chemical and mechanical polishing, what happens is there could be inherent defects in the structure of the wafer silicon itself. Such of those defects where, let us say, suppose at that point, let us say something, one track or a transistor gets manufactured at a place where there is a physical defect in the silicon. Obviously that device will that particular device and that particular chip would have gone bad, okay. And the number of good chips that come out is basically the yield. If you have got 900 good chips coming out of a wafer on which 1000 chips have been what should I say, shall I use the word printed? Yeah, chips are printed. So 1000 chips are printed, then the yield is only 90%, which is quite high at the beginning, okay. At the beginning, when a new process is put to use, okay, until the process stabilizes or matures, the yield will be typically low, maybe 60%, maybe 70% or so on. Therefore, initially when new chips in a newer technology are introduced, the cost of the chip will be high because the yield is low, and the amount of money that you have put in the manufacturing the chips will have to be amortized or distributed over a smaller number of chips. Therefore, the cost of each chip is going to go high. As the process matures, what will happen is these chips, the cost will gradually come down. Both the cost of manufacturing, the cost of testing also will come down gradually. Therefore, as the process matures, the chips become cheaper and cheaper. Okay. Then this is typically the response, and this is how it will be done. Yeah, there are different now I want to just see what are the different kinds of faults that can occur in a chip. The faults can be a stuck-at fault, it could be a delay fault. I was mentioning to you earlier, some minutes earlier, that whenever a chip experiences a little bit of overetching of the tracks, it is possible that two aluminum tracks, instead of being 1 micron wide or maybe 0.5 microns wide, may be only 0.35 microns wide or only 0.25 microns wide, in which case their resistance is going to be more. And if that happens to be on a critical path, then the RC time constant is increasing and the chip may not work at the desired frequency. There might be no stuck-at faults. Stuck-at faults, every node is toggling from a 0 to a 1, but they are not toggling in the required amount of time. Okay. It's like saying that an engineering student who goes into engineering is expected to come out in 4 years. Okay. But some of the students may take 5 years because of the backlogs, this, whatever it is, in which case they are not stuck in engineering, but they are taking a longer time than the prescribed time and the required time to come out of engineering. Therefore, there is a delay defect. Okay. Obviously, when there is a delay defect in a chip, this chip cannot be made to work at 500 megahertz. It may work only at 250 megahertz. And a processor which is made on a wafer, which is scheduled or which is planned, which is designated to work at 500 megahertz, may not work at 500 megahertz because of a delay defect. However, it is not thrown away because it is not entirely junk. It is put there, it is put to use, it is put in a different bin. It is this what is called binning, and therefore it's marked saying that it works at 250 megahertz and sold at a lower price. It's not completely junked. It cannot be junked. Okay. So that's the way testing also helps you to identify whether there are delay defects. If there are delay defects, yes, the chip is not entirely junk, but if there are stuck-at faults, yes, then the chip is completely means it is decided that it is bad and it cannot be used any further. Okay. Then there might be other kind of defects, like for example bridging faults, like two tracks running side by side, they get shorted to each other because of certain process defect. Okay. Such kinds of defects also need to be found out, and these defects can be found out either through a measurement of voltage, logic 0, logic 1, or through a measurement of current, because if there is a part that is defective, the current drawn may be higher or may be lower than what the expected value is. Okay. So these are the different type of faults in the fault. Every fault has got what is known as a fault model, which is actually used for verifying or testing those faults. We will go ahead with this in tomorrow's session. I will wrap up the DFT part in tomorrow's session, and then I will also talk a little bit about maybe physical design and a little bit about low power methodologies. So for now, it's enough for today. Okay, and we will meet tomorrow at the same time from 8:15 onwards. Till then, thank you very much for being with us today. Thank you.
MBBS చేయాలంటే ఇంటర్